Okay, let's get started. So can people see why I put those there? Can somebody tell me why I put those pictures there today? Actually, some people can read this, I know, right? Is there anybody who can read this? Good, okay. So you know the right language at least. But what's going on here? I mean, some of you should be able to figure out each of them. So this is King Bruce with his spider. You know the story of King Bruce, right? You know, he doesn't give up. Basically, the spider doesn't give up, so he decides he also shouldn't give up. This is a story from India. This is King Vikramarka, and this is coast guard Betala, and essentially he's supposed to bring him from some tree and take him somewhere. And every time he's doing this, Betala will tell him a story and ask him a question at the end. And if the moment he speaks, then the ghost will go away. And this thing will just keep going every night, okay? Because this guy doesn't learn a lesson. And this, of course, is a bad aspect ratio of Captain Ahab and and Moby Dick. And this is my Moby Dick, my laptop. So although we have messed up twice in the live class, I didn't give up yet. I got a new battery and I figured out how to do this, and famous last words. So we're continuing with this again. Okay. Okay. So one question before I start is something somebody asked, and I think it's a question worth asking ourselves. Exactly why doesn't value iteration get stuck in local minima? Okay. I mean, you have seen stories. I mean, of course, you're trying to maximize the value, which is sort of like minimizing something else. Okay, and typically we are always looking at pictures like this. Okay, and so if you are somehow, and what you are doing seems to be local changes. The value update in value iteration is doing local updates. Okay, so you're doing local search supposedly, and yet you're doing local search, and yet you're not getting stuck. Why? Of course, there's a theorem. The theorem says you are not getting stuck, but it's also important to have a good mental picture, good intuitive picture. So, does anybody have an idea as to why doesn't value iteration get stuck? Presumably, local minimas are local maximas. If you're interested in maximas, then why don't you get stuck here? Yeah.
Because information, so to speak, about where the maximas are travel throughout the entire system. So each location knows where to go, not for the local maximum, but for the global maximum.
Okay, so that's one thing. So that basically allows you to think that there still are actually local maximums. And somehow you are smart enough to get to the global maximum. That's a little too much to expect normally for a local search algorithm. Okay, I mean, I think you're in the right direction at least, but I want you to think of two things. Okay, first is this is a bad picture. Okay, this is sort of a trap you can fall into, because what is this? What am I supposedly showing here? It's a value, right? But value is not a single number. It's a vector. Vector of size S. First of all, if you are into the business of visualizing it, visualize a vector valued function. So in fact, what we are doing is we are taking a vector and mapping it into another vector. And these vectors are of size S. Okay, so, and the Bellman operation is taking a value and mapping it into a value. This value is a vector of size S, and this is a vector of size S. Okay, and what we showed to ourselves when we said Bellman has contraction property, right? We did talk about the contraction property of the Bellman operator. What we said is, irrespective of where you start from, okay, if you apply, so if you take some V1 and Bellman operator on V1 gets you, let's say, V2, okay, then what we were saying essentially is the difference between V1 and V star, which is the optimal value function. Okay, and the difference between V2 and V star. Okay, this difference is beta times this difference. So the two things that, first of all, I can't give you a picture. I'm only asking you not to have this picture in mind because this is a misleading picture. It's not that actually value function has lots and lots of local minimas. Okay, the right picture you have to have in mind is you're actually going from a vector to another vector, and you are not allowed to make any arbitrary change. In general, if I have a picture like this can be thought of as a vector of size 1. It's a scalar, where you can make moves from here to here to here. Any arbitrary moves can be made, but we are only allowing Bellman operation moves. Okay, and when you are making Bellman operation moves on the vectors of size S, then we know that by contraction property, these vectors will become closer and closer to V star. Okay, so in fact, people say that the value space is convex. They really, if you are using Bellman operator to move in it, then there only is one minimum, and you will eventually get there, or one maximum. You will eventually get there. Okay, so that's the picture you might want to have. Obviously, the actual reason, the actual convergence result itself is based on the contraction property. You need to understand why the contraction property works. Okay. The next thing, so then that's basically that. So the other thing I wanted to do before we go forward is actually to write down, just so that, I know this is more like an undergraduate thing to do than a graduate thing to do, but I'll try to write down at least one update, Bellman update, okay, just Bellman equation for maximization for the Bellman equation is always for V star, okay. We can write a Bellman equation for V star, and we can also write with respect to a given policy, just so that we know what we're talking about, okay. In particular, actually, if we go forward, okay, so this is what I showed you as the value V pi being connected to value V pi of S is connected to value V pi of S dash, where S dash is a neighbor of S, using this, right? This is, for most of you, probably this is obvious already what's happening. I'm just trying to write this down for a single example so that we are all on the same page, okay? So let's actually do that one at a time, since we talked about the policy. So there is a policy here, right? In this particular case, there is a policy. This is an MDP, and this is a policy here. Okay, so let's pick something. Let's pick this particular state. Okay, and we will write the Bellman equation for that state. So actually, the policy equation for that state, and then we'll talk about Bellman equation. Okay, the policy equation for that state would be what? So I want to write. So let's call this pi. This is the policy pi. Okay. And so I'm saying V pi of what is this state? It's 1, it's 2, 1 row column. Okay. Second, oh, sorry, you're right. Yeah, this is 2, 1. Okay. V pi of 2, 1. So the state name is 2, 1 because this is 2, 1. V pi of 2, 1 is equal to R of 2, 1 right? Okay. Now R of 2, 1 for us, if you remember, it's minus 0.04. Okay. Plus, okay, and then I'm in 2, I am going up because according to my policy, I'm supposed to go up. So if I try to go up, then with 0.8 probability, I will get into this state, in which case I will get V pi of 3, I'm sorry, 1, 3. Oh yeah, you're right, okay. That's true. We wrote it this way, yeah. 3, 1. Okay, plus with a 0.1 probability, I would try to go into this state, which in this turns out that actually that means you will stay here. Actually, I picked the bad state because this makes our equation too easy. Okay, but anyway, so in this case, it will be 0.1 times V pi of, once again, 2, 1, plus another 0.1 probability, I'll go that side, which will again leave me here. Okay, so that would be 0.1 times V pi of 2, 1. Right? Now, of course, this is my expected value times beta. If I'm doing infinite horizon Markov-Decision process, I need to have a beta. Let's say, beta is, let's say, 0.9 or something. Okay, so then this is 0.04 plus 0.9 times this whole sum. That's one equation. Okay, and this particular equation essentially will only be in terms of V pi 2, 1 and V pi 3, 1 because those are the only things that are there. Okay, and similarly you will write an equation you'll write an equation for this, you'll write an equation for this, you'll write an equation for this, and each one of the states. And when you write the equation for each one of the states, then you have n equations and unknowns, and there are linear equations. Right? Basically, in this particular case, this is, you can think of this as like x1, okay, and you can think of this as x2, and so you have a equation in terms of x1 and x2, okay, and then you have a bunch of linear equations and you're solving them, and when you solve them, you get the value of this policy. You see what I'm saying? You'll get the value of this policy. Okay, the other one that I want to do is, okay, so the other one I want to do is basically write the Bellman equation, not the policy evaluation, but the Bellman equation now. Okay, so in the case of Bellman equation, what I would have had is I wouldn't have known a policy at all. Right? Basically, this would be just an empty grid right now. Okay, I wouldn't know what action I'm doing anywhere. Okay, so in that particular case, let's try to write it, in the same thing because. Okay, so I'm going to now write V star of 2, 1. Again, for the same state, I'm writing the Bellman equation now. Okay, V star of 2, 1 is equal to, again, R of 2, 1. Okay, plus beta times, okay, and then max of first equation would be this whole thing, right? That's basically going up equation. And similarly, I need to write an equation for going down, another equation for going left, another equation for going right. Do you see what I'm saying? So I will have max of multiple equations with unknowns still. That's the Bellman equation. You get that, right? Okay. Yeah, there's somebody asked me a question.
You have 3 actions to do with the hot state, so we don't go down.
No, I think we have 4 actions. I mean, this is my old MDP. So you can go up, go down, go left, go right. I mean, it's an example issue. I mean, in this world, as I remember, I told you guys we had four actions. If you can always have an MDP with only 2 actions, in which case you just
so we just write
just do whichever actions you are possible that are possible. In fact, the interesting thing is that this is a particularly uniform MDP where in every state every action is doable, but that's not needed. That's not needed. You can essentially say that in some cases 4 actions are possible, some are 3, some are 9, some are 55, that's okay. And Bellman equation essentially requires you to write, a successor equation for each one of the actions. Do you see what I'm saying? Except, the only thing is that when I copy this over, might actually write this down. When I copy this over, what I would have written here, the first equation, beta of max, beta times max over A of, okay, where the action A is going up, okay, if it's up, then it's 0.8 star, 0.8 times V star, not V pi, V star 31 plus 0.2 times V star 21. Right? That's the first part. And then similarly, you need to write one for down and one for left, one for right. Okay, that's how these equations look. And when you're doing value update, you never actually write the equations yourself. You just basically are playing with the numbers directly. Okay? Right?
Sir, at state 0, 3, 5, 3, 1 will be.
What?
At 0 epoch. We're doing it for the first time. At that time, it will be minus 0.0.
It's up to you. No, so first of all, realize that Bellman equations for infinite horizon MDP don't say, there is no notion of V0. Basically, the Bellman equation for infinite horizon MDP is just a single set of equations. Let me go back and show you that. This is it. That's Bellman equation. Okay, it did not say what is V0. There is no point in talking about V0. V0 is a crutch that you use, because rather than directly, all Bellman is saying is figure out the values for V star for all the states such that this set of equations are satisfied. These are nonlinear equations. What you decided is rather than actually solve them, and as I said, in fact, there is a way of solving them by writing a linear programming encoding. I'd love to go here and talk about linear programming encoding, except I think only 2 students will understand LP encoding here. Okay, and in fact, you can write this as a linear programming encoding, and that's actually the only proof that computing MDP value function is a polynomial problem. Because there's, the way you show that something is polynomial is there exists at least one way of doing it in polynomial time. None of the ways I talk about in this class are polynomial. Value iteration, you don't know how many times it's going to iterate. There is no bound. Okay, policy iteration, in fact, value iteration, there is no bound at all. Okay, policy iteration that we'll be talking about in a minute has a bound, but the bound is a power s. That is exponential in the number of states. Okay, the only proof that in fact MDP for infinite horizon malcoordination processes, value iteration, and the value function can be computed in polynomial time is because this set of nonlinear equations can be solved by setting up a linear programming encoding. And since we know that linear programming encodings can be solved in polynomial time, that too is a crazy problem, right? I mean, you know that the most obviously, most practically used, I don't know how many of you know that, not those few people know. It's kind of weird that they sat separately. But I mean, they are from industrial engineering, so they actually know something about linear programming. But all of us should know, really. I just don't know how many things we will make up in one class. But one thing that's interesting is the most obvious algorithm that people used for linear programming. If you take a simple class on linear programming, the algorithm that you would be taught is the simplex algorithm. The simplex algorithm is actually exponential time worst time complexity. Okay, and the way to show that linear programming is polynomial is there exists a reasonably unintuitive, for those of you who know what simplex is, which sort of goes through the corners of a polytope, and the interior point algorithms, which start in the middle of the polytope and go towards the optimal one directly. Those can be shown to have worst case complexity that is polynomial. And for the longest time, for most reasonable sized problems, the so-called polynomial algorithm takes more time in runtime than the exponential simplex. Why? Because all you say in polynomial is, O of a polynomial, k times O of a polynomial plus another k dash. And this k and k dash can be humongous. All you know is as n increases without bound, every polynomial would be eventually overtaken by any random exponential. Okay, and in fact, most linear programming solvers still actually use, as far as I know, many of them still really use just the simplex algorithm. That's the one that you will get taught if you take a course, for example. That's exponential. But we do know that linear programming is polynomial. And since I can convert this into linear programming, I know that this is a polynomial problem. But we won't solve it by doing it, converting it to linear programming. Value iteration, just doing an iterative one. Okay, so going back to the question that one of you guys had as to what about V0? V0 has no semantic status. We only care about V stars. And you decided to come up with a V0, which is sort of a crutch for you. Like, for example, when this room was being built, I'm sure people put all sorts of random sticks and things in the middle to hold the room. But they have no final semantic status. In the end, this room has no such pillars. They're gone. To get to this room, you did this. So similarly, to get the iterative method to work, you essentially start with, you convert this equation into a iterative update equation. So in fact, Bellman equation is an equation. It's an equation. Okay, this is called Bellman equation. And what we are doing it here is this is actually not an equation. This is more of the computer science equality sign. This is an update. The right way to write this is that. You see what I'm saying? I mean, you are not saying Vk of S is equal to this. You are just saying Vk of S will be set to be equal to this value. This is an assignment. So this is Bellman update. And you're solving Bellman equations by doing a series of Bellman updates. And the neat thing is, irrespective of which V0 you start from, any random approximation to value function, you will get to V star. And that's again because Bellman update as an operator has the contraction property, which basically brings two vectors together. Okay? Yeah.
How do you bootstrap those values? Like if everything is dependent on the value of the neighbor and every neighbor.
No, I did not. I said you can pick any random values. There is no bootstrapping. So, okay, I have like a 8-state MDP, let's say. So I'm saying V0 would be 8 numbers. 8 numbers. Just give me some numbers. What do you want first number to be? 8? How hard is that? Second number, somebody else tell me. 7. Third number, 5. Fourth number, 5 by 4. Fifth number, 0. Sixth number, 95. There you go. I mean, of course, there should be 2 more. Okay. There's no bootstrap. Any random value function, I mean, you can initialize the value function to be any random value function. And you're guaranteed that this guy would be, let's say, far away, So this V0 minus V star might be quite high. But the moment you apply Bellman, update on this, V0 comes closer to V star. I mean, the V1 comes closer to V star. V2 will come even closer to V star. V3 comes even closer to V star. Now, the one question, of course, is if I'm smart and if I put the value function to be closer to V star to begin with, then the number of iterations can be fewer. That is indeed true. That is indeed true. So if you do spend some time and initialize the value function, more intelligently, the number of iterations that you spend would be fewer. But as far as the property of the algorithm, of termination property of the algorithm is concerned, it doesn't matter where you start from, you will terminate. And you will terminate, in infinite iterations. Asymptotically, you will terminate, that's all. Okay?
Set the reward for, so initially, does it make sense to set the value for each state as 0?
You can set it as, set it as 0, yes.
For every single tile, every single one.
Yeah, so here is an interesting question, actually. That's an interesting question. Do people see that even if you set it as 0, Bellman will somehow come back on right path? Because you don't get to change the rewards. The immediate rewards are what they are to begin with. Okay, just because you set V0 to be all zeros, it's not going to be the case that V1 will be all zeros. Okay, it's again, I think you have to try some of this stuff. Okay, and also you should follow the proof. If you're interested in making sure that you understood all possible angles of what the value iteration theorems are saying, you really need to read the theorems. I'm just giving you some background. Okay. Okay, so what I'm going to talk about next is policy iteration. So we did value iteration till now, and then we're going to do policy iteration. And in the case of policy iteration, the basic idea is there are infinite number of value functions, but there are only a power s number of policies. The optimal policy has to be one of these. So it seems reasonable to go through the policy space looking for the optimal guy than to go through the value space looking for the optimal value function. Okay, in particular, if you do policy iteration, you're guaranteed that unless you have zero memory and you don't remember that you have looked at a policy before, you never have to look at the same policy more than once. Suppose you evaluated a policy, you picked a policy. So essentially, the brute force method for policy evaluation would be this: loop for policy pi in a power s policies, evaluate pi. Okay, and keep track of the current maximum. And by the time the loop is over, whichever policy had the best value, you just give that out. Right? Okay, so even this, it's only going exponential number of iterations. Okay, so of course you can do much better than that. Rather than just loop from one policy to another policy where the two policies have no connection, what I would do in policy iteration is I will start with any arbitrary policy, and then find the next policy from the previous policy. I find the next policy by tweaking the previous policy. How do I do that? Essentially, so to do that, first of all, it's easy enough to start the loop by pick, policy pi 0. Okay, that's basically just like picking a value function. So except that it's even simpler in some sense. So for each of the states, you pick one of the actions and say that's the action for that state. That will give you a policy. Right? Now having picked the policy pi 0, you compute its value using the value equation. Okay. Now this, remember, these would be actually a set of linear equations. So for now, actually act as if you will solve these linear equations. You know, compared to some exponential thing you're about to do, solving linear equations looks like an easy thing. So you call a subroutine to solve the linear equations, you'll get the v pi 0. Okay. Now, having found the value, now that I know v pi 0, okay, so I went from pi 0 to v pi 0. I now ask, what is the greedy policy of v pi 0? This looks like magic, right? Why won't it be that if I go ask what is the greedy policy of v pi 0, why won't it be pi 0? That's the interesting part. It won't be. It won't be unless you are such a lucky guy that pi 0 was pi star. In which case you say, I'm done. So the point is, if you start from pi 0 and you compute, if you start from an initial policy and you compute its value, and then you computed the greedy policy corresponding to that value function. If it is the same as before, then you say that is the optimal policy. If not, you now have a new policy. You then go back, evaluate the policy, v pi 1, compute the greedy policy corresponding to the evaluated, the new value. So you keep doing this by changing the policy every time.
But we are also changing state.
What?
But we are also changing state.
What state?
We
There is no state. Remember again, whenever we write this, v is a vector. Pi is also a vector. The very important thing to keep in mind is MDP doesn't have an initial state. In fact, you would think that when somebody is trying to do planning, they would know where they are and they know where they want to go, they try to find a path. In MDPs, there is no such thing. Everybody needs a value. And everybody's final value is just as important. Again, I mean, these are good questions. I mean, the problem is, the first time you look at this kind of algorithms, I mean, they're like, one correct way of understanding it, maybe 5 correct ways of understanding it, 10 million bad ways, wrong ways of understanding it. I don't know which wrong way you have. And the only way is, this is where I put, I mean, first of all, you can ask me these things, that's good. But secondly, I also put that forum, but then of course the forum seems to show that everybody knows everything. Because it's completely silent. so I assume everybody knows everything. Yes?
So we get a new v pi 0 different from pi naught. Is it because that multiple policies can have the same value?
Exactly. And furthermore, think of what is happening actually. Think of what is happening. So when you went from pi 0 to v pi 0, you solved a set of linear equations. When you went from v pi 0 to the greedy policy, in doing greedy policy, you do a max operation. There's a sneaky thing going on here. Actually, if you are focusing on pi 0 becoming pi 1 becoming pi 2, I suggest you focus on v0 becoming v1 becoming v2. If you ignore pi's, v0 becoming v1 becoming v2 is Bellman update. That's the thing you want to convince yourself. Okay, it's like pi 0, v0, pi 1, v1, pi 2, v2. Because I said policy iteration, you are focusing on pi's. But focus on v's, v0 to v1. How did you go from v0 to v1? You can actually see that the step of going from v0 to pi 1 and from there to v2 is actually doing Bellman update. It's taking a max of the best actions and then computing the value. It's just splitting that Bellman update into 2 pieces. Once you understand this, it's not at all surprising that policy iteration has exactly the same beautiful properties that value iteration has. Those value functions that the policy iteration goes through, they will have the contraction property. They will become closer and closer to V star. The only difference is you are making bigger steps. Did you get this? I mean, I hope you get this, because this is the best way to understand policy iteration. Okay, policy iteration is making you look at the policies, but really what you should look at is the values that you're going through. And those values have Bellman updates relations. When you have Bellman update relation, then you are essentially doing contraction. It means you're becoming closer and closer to this. Yeah.
So if the greedy policy is not the optimal policy, we don't update. So I don't understand how do we update the policy here?
No. What do you mean? What do you mean I didn't update? So I started with pi 0 and I computed the value corresponding to pi 0. Then I computed the greedy policy corresponding to that value function. That's it. And if that is the same as pi 0, then I'm done. If it's not, then pi 1 is this. This is pi 1. And then, so actually I can write this as pi 0, and I'll say v pi 0 is evaluate pi 0. Evaluate pi 0 means do this, solve these equations. Okay? And then once I have v pi 0, then pi 1, the next policy is nothing but greedy policy of v pi 0. And you do remember what a greedy policy is. For every state, you compute, given the current values, for every state you compute which action will give the best expected value there, and pick that as the value. Pick that as the action. The cute thing is when you are computing the greedy policy, you did the max operation over expectations, except you only kept the A for which the max happened. If you just took the max, you would have been doing the Bellman update. Do you understand what I'm saying? So you just split what you were doing in value iteration into two pieces. And one piece becomes the new policy, the other piece is evaluating that policy. Okay, because of which, in essence, policy evaluation is guaranteed to, wow, I don't know what happened here. Yeah, so this is basically the policy iteration algorithm. You choose a random policy pi and you loop where you first evaluate current pi to get v pi. Okay, and then for each state in S, set pi dash s to be, the action that gives the best backed up expected value. You do this for each state separately. Right? Having done this, now you got pi dash. Now replace pi with pi dash. Go back to the loop. And you keep doing it until there is no difference between pi and pi dash. If there is a difference between pi and pi dash, in fact they differ at least in one dimension. These are s-dimensional vectors. There are as many dimensions as the number of states. If the policies agree on all the dimensions, then obviously they're the same policy. Then you are never going to change anymore. So you never stop. Now the interesting question, of course, is how did I not get stuck with an inoptimal policy? That should be a worry. And the reason you did not get stuck with an inoptimal policy is because underneath it all, you are essentially doing Bellman update on the value functions. And since they have contraction property, you're guaranteed that in every step, you are going to improve the policy. It will monotonically improve the policy. And one of the neat things, I know that there was a question, but let me just point one thing out. One of the neat things is, suppose you are considering, as I think I showed this last time, suppose you're considering the number of iterations. As the number of iterations continue, okay, how close is the current value function to the true value function? And how close is the current policy to the true policy? Okay, and if you draw both of them, you are likely to find that the value function might kind of fall like that. value residual. That means this is the difference between the initial value, the current value function and V star. Okay, whereas this is the number of iterations as the iterations keep going. Okay, whereas the policies, in fact, you could do this. The question, of course, is, so let me complete it. So the policies might go, let me see a different color. I'm sort of drunk with this power of colors. Okay, the policies might go like that. So the policy, I hope there's no, there's a slight, what I meant to say is that there is no, basically the policies would reach optimal policy much faster than the value reaching the optimal value. And you could do this either in the context of policy evaluation or in the value iteration. So as value iteration, you could do this with respect to your little code you're going to write. As the value iteration is going from iteration to iteration, at each point you know what the policy is. I know that value iteration doesn't care about what the policy is until you reach V star. But I mentioned last class that at any time you have a current value function. And the policy that if you are stopping then the policy you would use is the greedy policy with respect to that value function. So you can keep track of, in the value iteration, as the number of iterations go, you can keep track of what is the current greedy policy. And you can compute that guy's value and see how far is that from V star. And what this purple thingy is saying is that the policy stopped changing way before you realize that the value function is not changing. Do you understand what I'm saying? And having realized this, then you realize, hey, you should be doing policy iteration. Let's think in terms of policies rather than values. Okay? Yeah. First of all, there was a question. You still have a question?
So I noticed that when I was doing the homework, and I was wondering, I know that they both have different termination conditions for the loops, but like mathematically, under the hood in quotes or whatever, they seem like the same.
Yeah.
I was wondering if there's a more substantive difference that I'm like missing besides.
No, the point is they're mathematically the same, but you are going from policy to policy here. In the value iteration, you don't think of policy at all. The next value function, there is a substantial difference in the following sense. It turns out that for this to work, you need to basically, so the value iteration, it turns out, is the bedrock of MDPs. If you come up with a new MDP, which will be coming in a few minutes because we'll be talking about stochastic shortest path, you will always be able to come up with the value iteration algorithm for it. It's not always guaranteed that you can come up with a policy iteration algorithm. Why? Because value iteration algorithm is completely insensitive to the initial value function you started from. Policy iteration also is completely insensitive for infinite horizon MDPs. It's not so for stochastic shortest path. It turns out, and in case, since you seem to actually be keeping track and doing homework, it's those of you who haven't been doing should be depressed. And you would basically probably also read ahead and found that there is this notion of proper policies we'll talk about for stochastic shortest path. And unless you pick a proper policy as the initial policy, if you do policy iteration starting from an improper policy, you just diverge away in the context of stochastic shortest path. Whereas for infinite horizon MDPs, this problem doesn't exist at all. Because the beta is our guard, it's going to make sure that everything is proper. The discount helps. Okay? There's some pictures here. I'm not going to show much, but this is sort of some kind of a visualization of what is happening in the policy space as well as how the value is changing. Remember, value is a vector function, really. So that's the only way you can show it. Anyway. So that's some notes on policy iteration. each step of policy iteration is guaranteed to strictly improve the policy, and that's basically because of your the Bellman update contraction property. Convergence is assured, and in some sense, it's cute that convergence is assured, but it's obvious also it should be because they only exponential number of policies, and it will give you the exact value for the optimal policy. And what's interesting is that complexity wise, this is of the two algorithms you have seen, value iteration worst case complexity is what? We don't know what is the number of expected iterations. Okay, whereas for this guy, we know the number of expected iterations. The number of expected iterations is only a power s. So policy iteration is at least exponential. This also kind of should make you, I mean, now that you are grad students and you care about these sorts of things, I talked about 3 approaches, okay? LP approach, which I didn't tell you exactly how to do it, although if you look at the Mausam book, he has a little explanation of how to convert the Bellman equations into a LP encoding. Okay, that is guaranteed to be polynomial, worst case. Okay, then there is value iteration. Okay, which is actually I would write this way. So LP, which is guaranteed polynomial. There is value, and there is policy iteration. Guarantee is exponential. And then value iteration, no guarantees. Complexity wise. Now, if you were to take any reasonable sized MDP and try to solve them using these 3 algorithms, you cannot necessarily, I mean, if you don't understand worst case complexity, you would think, well, this guy is going to be done very fast, and this guy may never get done. Actually, for most reasonable sized MDPs, value iteration terminates way before policy iteration. Both of them terminate before linear programming encoding. Because linear programming encoding is going to have huge constraints. Okay, that's the reality. It's cute to know, basically. This is the only proof we have that this is a polynomial problem, but if you were to use this, people will laugh at you mostly. Because it's not the best way to solve the problem. Okay. In practice, there should be, I mean, obviously, given if you're going for really large size MDPs, eventually this is going to down. But it's dead already anyway. For any given, the point is we don't actually. Basically, for most normal sized MDPs, this actually does well. Quite a bit well. But that's what we're going to talk about, I think, somewhere here. At most empirically, so although you might need exponential number of iterations, in most cases people found that empirically you seem to only need about n iterations, where n is the number of steps. You don't need to really go to a power s. That's a very few iterations. However, people also found that if you do intelligent value iteration, prioritize sweeping, for example, update the values of the states that are likely to change. Okay, initialize the value function with a good value approximation. Then value iteration is actually a pretty complicated one. Okay. And again, there is no polynomial bound on the number of policy iterations. The only reason we think that MDP is polynomial is because of this. First of all, actually, that's a good question. I mean, the fact that only I am laughing and nobody else is could either make me a madman or that you are not following the class. Okay. The interesting thing is that actually a lot of interesting algorithmics is compilations. You take some problem, compile it to some other problem. Okay. So LP, you take courses on how to solve LP encodings, and here we just said, basically combined into LP, so it's polynomial. I mean, you know the mathematician joke, right? That Mathematicians always want to just say, we reduced it to an already solved problem. And so we're done. And so the classic joke, in case you haven't heard it, there's this mathematician who is one day sleeping and was smoking cigarettes and then fell asleep and then found suddenly in the middle of the night the smoke alarm was going off, and so he sees that the bed sheets are on fire and there is a big glass which should have water. He would have doused the fire, except the glass doesn't have water right now. So he had to get up, walk all the way to the bathroom, fill the glass with water, come back, pour it on the fire, douse it, go to sleep. A couple of days later, because this guy still drinks and still smokes, same thing happened again. He woke up, except this time there was a glass with water. So he threw the water down on the floor and said, now it's been reduced to an already solved problem, and went back to sleep. Okay, so, and you need to understand that, because from a mathematics point of view, you went back to, the LP essentially we know is polynomial. And I take this problem, convert it into LP, I can give you the proof that it's polynomial. Is that the right way to do it? Of course not, maybe not. In this particular case, obviously it's not the right way to do it, okay? So your question is, can you convert LP into MDP? Yes, of course, every polynomial problem can be reconverted into another polynomial problem. This is about, you're talking about reductions, basically.
Yeah, but then since value iteration is faster in practice, then why don't they use that first?
That is, no, first of all, that's actually, so there are, well, how do I say this? First of all, this is, many problems get converted into LP. LP, encoding has gotten a lot of people spend time, thinking about how to improve linear programming solvers, okay? And many different problems get converted eventually into LP. And each of those problems might sometimes have special structure, and one can ask the question, so, if that special structure is there, why can't we take some of those ideas and put them into LP? It's a reasonable question to ask. Some such transfers have taken place. One which I might talk, by permitting, is not between MDP and LP, but constraint satisfaction and linear programming and integer programming. We'll talk about, I think the second part of the course, we'll talk about constraint satisfaction problems. And it turns out CSP problems are essentially, complexity-wise, identical to integer programming problems, because both are NP complete. And furthermore, you can convert an IP, you can convert a CSP into an IP, you can convert an IP into a CSP. However, CSP as a field largely developed separately from LP and IP as a field. And in LP and IP, they have come up with all kinds of ideas such as cutting plates, which some of the people who know IP, for example, would know. And there are equivalent ideas in CSP, such as no goods. And there are some people who are smart enough to actually look at both of these and say, hey, there are actually cross-fertilization possibilities. And that sort of a thing has happened. Okay. So it's not a particularly, it's a reasonable question to worry about. I don't think you would do it because value iteration is faster. In this particular case, actually, all I needed to do to show polynomial time complexity of MDPs is to show that there exists a polynomially sized LP encoding. That's all. It doesn't even have to be the best polynomially sized LP encoding. You see what I'm saying? My interest is theoretical. I just wanted to show that it's polynomial, and then I'll move on. Okay, if you are interested in a practice, then you need to care about, did you get the best polynomial size encoding, for example. Okay. But in general, I do want you to think of this whole notion of compilation. You compile problems into other problems. Okay. Until now, you compiled high-level languages into low-level languages. But really, what you would be doing is compiling one type of combinatorial problem into another type of combinatorial problem. Why? Because you have a solver for the second one. That's it. Oftentimes. Okay. So value iteration versus policy iteration, which is faster, it depends. That's the great idea. And even though it looks as if it shouldn't depend. It should be that policy iteration always wins. The problem is policy iteration has fewer iterations, but each iteration is quite costly because you have to solve a huge number of linear equations. You forgot about that. You're just thinking about the number of iterations, but each iteration cost is quite high. Value iteration, on the other hand, is quite cheap per iteration, but it has many, many iterations. Now, which one is better? And all of a sudden, it doesn't look as obvious. Not surprisingly, if you take a random problem, sometimes value iteration is better, sometimes policy iteration is better. However, when you understand, so policy iteration must perform, PI must perform policy evaluation on each step, which involves solving a linear system. Now, the question, of course, is that's what is taking a lot of time. Do I really care as to what is the true value of my current policy? If I care, then I have to solve these, equations exactly. So one thing that I always ask you to think about is, in many cases, you have a big problem that you want to solve, and you write a multi-step algorithm. This multi-step algorithm is an iterative algorithm to solve this big problem exactly, supposedly. If you ever find yourself spending your lifetime making the 14th step of this particular thing optimal, exactly optimal, ask yourself, what the heck am I doing? Ultimately, nobody gives you a badge because the 14th step of your algorithm did faster than 14th step of somebody else's algorithm. They'll give you a badge because your entire algorithm did better than the other guy's algorithm. That's it. You see what I'm saying? So it's very easy, and I say this because, again, in AI, it's been done in general, lots of fields it's been done, that people, once they get a problem, they'll forget where the problem came from. And then they'll focus on, let's just try to optimize, let's find the optimal solution for this. That means, let's get the exact values corresponding to V pi. How do I get the exact values corresponding to V pi? Oh, what the heck, there is this Gauss-Jordan elimination algorithm, computing matrix inverses, and then, I can start using those. But do I really need the exact value of the policy? The entire thing is approximating one policy to the next policy anyway. Do I really need exact value? It turns out you don't. All you need is that the next policy is slightly different. Think about it this way. Value iteration worked. Value iteration worked. Value iteration takes more number of iterations than there are number of policies sometimes. So from one iteration to next iteration, sometimes value iteration has not changed the policy. Did this make sense to you? And yet, it went on fine. That means basically, you can actually, as long as the value changes in some place, you're making progress. The policy may not still change, but the value changed, so you can make progress. And because of which, it turns out that you don't need to solve these equations exactly. You can solve them approximately. Now, how do I solve equations approximately? How do I solve a set of linear equations approximately? Well, I will use value iteration. If this does not, spin your head, I don't know what does. Okay, so we started with value iteration, and we said instead of value iteration, we'll do policy iteration. Now we are saying to evaluate the policy, we will use value iteration. Now, value iteration actually does iteration over the Bellman updates. When you are doing value iteration for computing the policy value, you would actually be doing updates only on the single equations. There is no max anymore. Do you see what I'm saying? So all I would do is another way, it turns out, I did not say this before, but another way of computing the value of any policy, I don't know, it will take a while to me. The value of any policy is basically, so if let's say I have this policy and I want to compute the value, I said set up the linear equations and then solve them. Another way is give some numbers to values of this policy, and then everybody looks around its neighbors, knows which action it's supposed to do, and does that action, simulates that action, updates its value function, and it keeps doing it until its value doesn't change. Just looks like Bellman update, except except you're not considering all actions, you're only considering the action that you're supposed to be doing. You don't need to write a new piece of code. It's the same value iteration code. It just doesn't have to, the previous value iteration code said, for every action that is doable, compute the expected value that comes, take the max of it. Now, every action that is doable is the only action that the policy allows you to do. Just do it and take the max of, that's one thing, that's it. So you don't actually have to change the code. It's the same value iteration. That's why people say you're running the value iteration a few times to compute the policy's value. All that does is it makes your value approximation slightly better. Then you try to see what the value policy is here. So they take the greedy policy corresponding to that value function and then do this. Okay, so all I'm doing is this is what's called a modified policy iteration. And in modified policy iteration, all I would do is I will, instead of actually solving the set of linear equations, I can just run the value iteration a few times. That's modified policy iteration. Okay, and that's better than policy iteration. Once again, because it avoids trying to get the exact value of a policy. And getting the exact value of the policy, you don't necessarily get a badge. Now, if you want to ask yourself, why does modified policy iteration supposed to work? Once again, go back to the fact that value iteration works. And in the value iteration, you can start from V0 to V1 to V2 to V3, and there can be a run of 15 value functions, all of which corresponds to the same greedy policy. So the policy iteration guys will be thinking you're wasting your life. You're not doing anything. But we know we're doing something. We are becoming, in the max norm sense, closer to V star. If that's enough to make value iteration converge, modified policy iteration also will converge. Okay? Okay, and then as I said, value iteration, it turns out, is actually more robust. For any random new MDP you come up with, and there are tons and tons of them, you first understand how to do the value iteration. And we will do it, for example, for stochastic shortest path, value iteration is easy, policy iteration is hard. When we get to POM-DPs, it looks as if we may never get there, but when we get to POM-DPs, value iteration is what we'll do in POM-DPs. Okay, so there is a reason for all these things. And then actually the bedrock, the convergence principles, convergence theorems, etc. come from the value iteration. The policy iteration looks quite different syntactically, but it's actually just doing bigger steps in the same space. Yes?
So policy iteration also depends on the Bellman update. Why isn't it supposed to converge?
It is converging. They converge.
It's not guaranteed.
No, it's guaranteed. For infinite horizon MDPs, it is guaranteed. This next one that I'm going to talk about, it's not guaranteed. Okay, indefinite horizon MDPs. Okay, so we have talked about finite horizon MDPs. We have talked about infinite horizon MDPs. The models are slightly different, right? In the case of infinite horizon MDPs, you had to talk about this, discount factor, and you didn't have to talk about number, and you didn't have to talk about the horizon. In the case of finite horizon MDP, you had to talk about the horizon, but didn't have to talk about discount factor. So there's a lot that's common, but they're also different. The models are quite more different. So now the question is, in this case, each behavior sequence is guaranteed finite. Each behavior sequence is exactly t steps long, not t steps long. Right? In this case, behavior sequences can be infinitely long, but there is beta. Discount factor takes care of summing them to finite. Now, what we would like to say is, in many cases, we neither have known finite or known infinite. Known finite horizon, nor do we want to talk about infinite horizon. It's finite, but we don't know exactly how long it will take for this to. It's guaranteed that in some finite number of steps, you will fall into the goal, to a terminal state. After that, no more behavior is possible. But you don't know how many steps it will take. Okay, so we want to talk about a model that allows you to not discount future with respect to present. Because again, as I guess as articulate an argument as I made last time about how discount is way of life, etc. You could be, you don't care about human life. You might be using this for some other problem where it doesn't make sense to discount future rewards to current rewards. Okay? It's not necessarily the case that if I'm giving you $10 today, $10 tomorrow, $10 day after tomorrow, you would think that that's less than $30. If I say $10 today, $10 10 years from now, $10 20 years from now, you may not think that's $30. But if I say 3 days, next to each other, you may think, oh, that's $30. Even I can live that. Okay, so depending on your setup, you might actually not want to discount future at all. And if you don't discount future, and if you don't have a finite horizon, if you don't know the length of the horizon, then how do you deal with the problem? Okay, so if you don't have discount factor, then you cannot allow infinite horizon at all. Okay, and so we do have finite horizon, it's just indefinite. And so the question is, what's the best way to view such problems? And that is where we talk about stochastic shortest path Markov-Decision processes. It's just a generalization of, it's kind of connected to the two MDPs we talked about, and in a minute we'll actually show that it has the compilation property. That means if you give me an infinite horizon MDP, I can write a finite horizon, I can write a stochastic shortest path MDP that's equivalent to this. And similarly, if you give me a finite horizon MDP, I can write a stochastic shortest path MDP that's equivalent to this. So that means the picture essentially is this is SSP, this is finite horizon MDP, this is infinite horizon MDP. As I told you, I will tell you, how to compile it. Okay, and the other interesting thing is it also makes you realize the close connection, stochastic shortest path MDPs. Notice, until now, we were talking about maximizing value. The whole metaphor we are using is maximizing the value. But now I'll be talking about minimizing the cost. Shortest path means minimizing the path length, right? Minimizing the path cost. So shortest path MDPs, these basically, when you understand this, you have a direct connection to A star search. That's another plus point. You may have been seeing connections between MDPs and A star search as we have gone through. But A star search thinks in terms of costs and minimizing the costs. And MDPs have been talking about values and maximizing the values. Okay, mathematically you could kind of see that they are connected, but this particular SSP just makes it very clear that they are quite well connected. Okay, so what is the SSP? It's basically you do have a set of states, which is a finite state space. Okay, and you have a finite action set. Okay, and you do have a transition function just like this. All of this are common until now, the same as before, right? And then what else? Now instead of reward, we tend to talk about costs. Okay, and furthermore, actually I did mention that while rewards can be, you can say reward, a state has a specific reward, and normally you want to actually talk about not the reward of a state or a cost of a state, but the cost of doing an action in that state. Do you see what I'm saying? So basically, if you are in state S, and you did action A, which can take you to 3 different states, S1, S2, S3, let's say 0.7, 0.1, and 0.2, right? Previously, what you would have done is you would have taken R of S and added it to the expected value you can get over this action set. Okay, now instead of R of S, I would say C of doing action A in S. Because remember, I'm doing action A in the state S. So I will assume that there is a number corresponding to cost of doing any action in any state. Okay, now this is beautiful because if C of AS can be defined to be C dash of just A. At a function, a two-value function can be defined, a two-input function can be defined to be equal to a one-input function. That means you basically, you take A and S, but really you only care about the cost of A and give that number. So cost is the same irrespective of which state you do it. If you do that, that's your A star search. Right? Because the A star search, each operator has a different cost. And you're trying to find the path that is shortest in terms of adding the cost of all the operators. So C of AS is even more general than A star. It's certainly in the same direction as A star. It's also minimizing cost. But in fact, I'll also allow you, if you want, you can say action A has 2 units cost if you do it in state S1 and 4 units cost, do it in S2 and so on. Okay, so just like instead of giving R, I'm giving the C function. So it takes, actually, in fact, the way this is written, it's basically taking, you are doing you're doing action A in S to get to S dash. I'm giving a cost to that. It's even more general than this. It's up to you. Okay, but in general, as long as you understand that we're talking about cost, that's good enough. Okay. And then, so this is a difference, but this is a syntactic difference, really. Because, I mean, you can always convert rewards, take the negative of the reward and say that's a cost. And if you minimize that, you have maximized the cumulative. Up until now, really, there is no major difference. Okay, there's a syntactic difference, but there's no major difference. This is where things become interesting. Stochastic shortest path algorithms must have goal states. A goal state is a state of nirvana. Once you reach that state, you can't go anywhere else. And you will forever get zero cost. Remember, this MDP has no reward, it's only cost. Right? And so a goal state is nirvana. I mean, just like Buddhists say that once you reach nirvana, there is no more pain. Okay, no more cost. Okay, now you notice that such a state could have existed in your previous MDPs, but it was not part of the definition. In FormDP, you could have had states where once you reach the state, you no longer get any cost, and you can't do any actions. You could have done that in the finite horizon MDPs. You could have done that. In the infinite horizon MDPs, also you could have done that. But it wasn't required. It was not a definition that the MDP must have such states. The picture I had such states. Right? The grid I had did have the goal states were terminating. So that's what this is. Okay, so G is a set of absorbing cost-free goal states. If that's basically called a stochastic shortest path algorithm. Stochastic shortest path MDP. Okay, now here's my question. Remember the grid I had? Does it satisfy all these properties? It does have goal states. I can make the reward into cost. It basically it satisfies this. Okay. Oh, okay, so that's true, but that could have been changed. I mean, syntactically it could have been changed. So the point he's making is when you reach the goal state, you got $10 reward and then no more after that. In SSP, when you get to goal, zero cost and it will be zero forever. Still a kind of a, mostly syntactic difference. You can get it up. Okay, the thing that, so it's almost fine. What I want to get you to understand before we leave for today is such an MDP, the question is, does it always have an optimal policy? The thing that, if you take a course on organization policies, in math department, you would probably still be in the place where we are proving existence of optimal policies for even finite horizon, let alone infinite horizon. Okay, I just said such theorems exist, and you believed me, and then we moved on, right? And the question is, will optimal policies exist? Will optimal policies exist for stochastic shortest path MDPs as defined this way? And it turns out that there are theorems proving that under two conditions, they do. So not every MDP which satisfies these conditions is guaranteed to have an optimal policy. If there is no optimal policy, then how do you find it? Okay. How does something not have an optimal policy? One way is all policies are degenerate. They're all infinity values, in which case there is nothing to compare it between one policy and another policy. Okay, are infinite cost. Okay, so the two interesting properties are, one is that there exists at least one proper policy. There exists at least one proper policy for this world. Now, what is a proper policy? A proper policy is one which, if you execute that proper policy, you have probability, one, that you will eventually reach the goal state. It's not probability one that you will reach the goal state in 5 steps or 15 steps or 25 steps. It's probability one that you will eventually reach the goal state, one of the goal states. Okay, have you seen improper policies? Remember, your priests were unhappy because you tried to avoid the 6 states. Right? Do everything to avoid the goals, because life is so good that you don't want to actually reach either the good goal state or the bad goal state. What? Yeah, but what I'm saying is you did see a policy that was improper. Okay, so, but the question is, I can generate MDPs where, where in fact there may be all policies are improper. In which case, there is no point in talking about optimal policy. If there exists at least one proper policy, then you are in business. Okay, so there should be at least one proper policy, and it turns out, and this is actually a tricky thing to convince yourself, that if there exist dead-end states. So SSP differentiates between, when we were talking about the grid algorithm grid example last time, we just talked about sync states. There was a plus 10 sync state, and there was minus 10 sync state. SSP did talk about absorbing cost-free goal states. But SSP never had states that are non-goal state, but once you reach there, you can't do any more actions. So the only way SSP will stop you, this particular, if you only have these kind of absorbing states, the only way you would be unable to do any more actions is because you already reached the goal. A dead end is called a dead end. I mean, it's like nobody ever says, Bill Gates never said, man, I reached my dead end. I made $40 billion, and I'm dead end. How can you say that? Okay, you reach nirvana. It's true that you can't do anything anymore, but you reach as good a state as you can get. Whereas I just got run over by a car, I reached dead end. That means I can't do any more actions, and I haven't reached a good state. in my grid example, I had dead-end states. If you have a dead-end state, you can have improper policies. It turns out. Okay, and so if you do not have any dead-end states, then there is a guarantee that there exists at least one proper policy. And once you have a proper policy, and it also is the case that every improper policy becomes degenerate. That means it eventually incurs a cost of infinity starting from any state. Okay, in that case, then none of the improper policies can ever be an optimal policy, because if you are incurring infinite cost from any state, then how can you be optimal? Unless everybody is incurring infinite cost, in which case there is no point in talking about optimal policies. Under those two conditions, it can be shown that stochastic shortest path MDPs will have an optimal policy. And when we come back, I'll basically just say that that optimal policy can be found by value iteration, where the value iteration now would be thinking in terms of cost instead of rewards. That's very small difference. And minimization instead of maximization. Remember the Bellman update, you had a max function. Now because we're talking about cost, we'll have a min operation. And then Bellman update will actually get you the optimal value function. Policy iteration, on the other hand, is not guaranteed to hold unless you start with a proper policy. But it turns out finding a proper policy itself is hard. Initializing it yourself with a proper policy can be arbitrarily hard. So that's why nobody actually tries. I mean, basically you don't think of policy iteration for SSPs as a killer. Okay. We can also talk a little about the connection between these and